All right. So we're here for AP Physics, work kinetic energy theorem 1, doing problem 2. A 100-gram bullet is fired from a rifle having a barrel 60 centimeters long. Assuming the origin is placed where the bullet starts to move, the force on the bullet by expanding gases follows the equation. You know, we're going to make this, for clarity, I need to fix this. This is meant to be the total force on the bullet along the barrel, not just the force from the expanding gases behind it, but all the forces in the x-axis. This is the total. Okay, given by the function 15,000 plus 10,000 x minus 25,000 x squared, where f is in newtons and x is in meters. Find the work done on the bullet. So I'm going through my little procedure here. I always start with a sketch of the situation. All right, let's see here. Right. Anyway, okay, so I have my bullet here in the barrel of the gun, right? Okay. We're going to fire that bullet. It's going to go from here. It's going to go down that 60 centimeter barrel. So this displacement is going to be 0.6 meters, right? Because we always want to go to meters. And we want to know the work done by that force on the bullet. That force, big F, pushing it along through that delta x. And so that is the plan. So we are going from here to here, right? Okay, from like x equals 0 to x equals 0.6. There we go. All right. So we, of course, part A, one of the work done. And so we say, okay, work, that's going to be our integral of f dot dx. They gave us an equation for that work, for that force, I mean. They told us that the force is given by the function 15,000 plus 10,000x minus 25,000 x squared. All right. Here we go, dot dx. I'm just going to jump right into it right away and say, hey, I can see that this force, as we move along, as x changes, that force is going to be changing, right? And so we have to use the integral form. We cannot simplify it out to f dot delta x. That force is going to be changing as we go, so we have to take the integral under that curve. We're going to be doing area under the curve through that integral. Going to be doing this. Hey, let's take care of this cosine theta, right? All right, would be there, and then times dx. Now, I'm going to do something tricky, all right? This force right now is defined in terms of x, right? And this equation, you see I've got positive term, negative term. In other words, the sign on the force, if the force is going with the motion is in the positive direction here, right? If the force is in the positive direction, I'm going to get a positive out, and then I'll have a positive, and my mode dx is always positive, so I'm going to get a positive. So, but if the force switches around to be negative, then it'll be going against the motion. I'll be getting negative work. The point is, the cosine theta business, it's always in this problem as we go along here. The force is either going to be this way or it's going to be this way. It's always going to be either if it's going with the motion, cosine of 0 would be +1. If it's going against the motion, cosine of 180 would be -1. The point is, if this flips around and go back, the sign on the force is going to flip to be negative. So essentially, the cosine theta, I could take absolute value of f times cosine theta times absolute value dx and let the cosine theta take care of the plus or minus sign. But the thing is, the force is always going to be the correct sign anyway for me. So I can leave that out here. Do you see that? Because the force is just going, this is just my force is going to be going along the motion. So it's going to be cosine of 0 degrees, which is +1, or cosine of 180, which is -1. And the sign is going to be taken care of by the sign of this anyway. So I'm just going to kind of leave that out. Is that okay with you? I hope that's okay. All right. dx is always going to be a positive value as we go to the right, right? So this will be negative when I need the sign on the work to be negative. So it's going to be fine leaving it like this. All right. So the cosine theta is going to be either cosine of 0 degrees equals +1, or cosine of 180 degrees equals -1. But it turns out whenever this is -1, the force is going to be negative anyway. And whenever this is positive, when the force is going to be positive anyway. And so like the direction of the force is going to be the same as the direction of the sign that we want will be, you get it, but we get it. So I'm just going to leave, in this case, I can get away with it with leaving that cosine theta out. All right. Since this will agree with the sign of F, I'm just not going to put the absolute values on the force. I'm going to let the sign of the force take care of it all at the same time for me. Otherwise, what I would have to do, if I have some function that's changing from positive to negative, is I would have to like do it piecewise. You know what I'm saying? If I had some kind of a force versus position, I'm trying to take the area under the graph, and I had some graph that like wandered from positive to negative, whatever, I would have to, maybe it goes back positive again or something, I would have to do this piecewise. I would have to chop it up and take my areas, you know, if I wanted to find the work done when I get to here, I'd have to kind of chop it up into like separate areas and stuff. You know what I mean? Anyway, you get it. If I was really going to apply that cosine theta properly, you know, because I'm taking absolute value of this, I'd have to like the force, I'd have to manually then do it and have my cosine be 0 here, then have my cosine be 180 here, then have my, you know, you get it. But I can get away with it in this case, not having to do that. So I'm going to take advantage of that. Okay. All right. So that's it. So I'm going to do this from my bounds on my integral. I'm going to go from x equals 0 to x equals 0.6 meters. So that's the integral I have to take. When I integrate things, I'm doing a derivative in reverse. So 15,000, that would have been, you say, 15,000x. And 10,000x, well, see, the x would have been an x squared, but it would kick a 1/2 out. But you say, but I don't have, it would kick a 2 out in front, right? If I took the derivative of this, we kick a 2. There's not a 2 there. There's 10,000. So there must have already been a 5,000 in front of it. See? Because 2 times 5,000 is 10,000. Okay, and then this one, x squared would have been like an x cubed. But if I took the derivative of x cubed, it would kick a 3 out in front. But I don't have a 3. I've got 25,000. So that'll be like 25,000 over 3, right? And that's minus there, right? Okay, so that's my integral. I want to evaluate that from 0 to 0.6, right? Because it's a definite integral with those bounds. That's why I didn't have to do the plus c business, because it was a definite integral. Plus c's would cancel out. All right, so the easy part is I'm going to do it with 0.6, and then I'm going to subtract what I get when I put 0 in. When I put 0 in, I'm just going to get 0. So it's really just going to be that putting 0.6 in for x. So if I do that, I'll get 15,000 times 0.6 plus 5,000 times 0.6 minus 25,000 divided by 3 times 0.6. And what I got out of that was 7,000 joules. Okay, so that was the work done on the bullet by this force as it goes down the barrel. All right, so we did 7,000 joules of work, which means if this thing started at rest, it gained 7,000 joules of energy. That's the energy in that flying bullet that's heading towards the target. All right, moving on. Let's go to part B. All right, okay, that's my work. Okay, part B says, okay, what if the barrel was 2 meters long? Now how much work is done? Well, aren't I just going to do the same calculation, except now my bounds are going to go from 0 to 2 meters, right? And by the way, if this is 0.6, 2 meters means the barrel is like this long. That's ridiculous, right? But anyway, so my work is just going to be the same setup. It's just my bounds are different, okay? So it's like same but new bounds. It's going to be the integral from 0 to 2 of blah, 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 dx, right? Okay. So I'm just gonna just go ahead. I'm gonna jump right to this point. You know what I mean? And plug 2 in. Can I do that in my head? Almost. Let's see. Am I gonna? So it's gonna be like. Let's see here. We'll have. Here, I'll just write it out. 15,000 times 2 plus 5,000 times 2 squared minus. Oops. Well, it's really sloppy, Dave. Good thing you can hear me say it. 25,000 divided by 3 times 2 cubed. Yeah, I'm going to be plugging that in my calculator. Why put myself through those mental gymnastics? All right, so here we go. So it'll be 30,000 plus for 20,000. Okay, that's not bad. This is the hard part. Well, actually, 8 times 25,000, you say that's minus 200,000 divided by 3. All right, so maybe I could have done it in my head. But anyway, 20,000 divided by 3. Yeah, so this is going to be 50,000 minus 66,667. You say that's going to give me minus 16,667 joules. And so we get that work done to be a negative value. And you're like, what? Why is that coming out to be a negative? You say, well, work is the amount of energy that's been transferred to the bullet. This is saying overall, we have taken energy away from the bullet. Like, well, wait. This is supposed to be the change. We're supposed to be changing the kinetic energy, right? Okay, work is the change in kinetic. And you say, wait a minute. You say the change in kinetic, but wait, isn't kinetic energy like 1/2 mv final squared minus 1/2 mv initial squared? That's my change. But the starting velocity was 0, so this whole term is going to drop. You say, no, wait a minute. Mass, it's 100 grams. Mass has to be a positive value, right? 100 grams, 0.1 kilograms. The final velocity squared, something squared, that has to be a positive, right? How can I have this minus 16,666 equal, you know what I mean? I'm going to get an imaginary answer for my velocity if I did that calculation. So what does that mean? Well, what that means, my friends, is that bullet will never make it to the end of that 2-meter long barrel. This force that goes against it, you see how as this x gets bigger, this negative term, right, is going to, because it's squared, right? This is going to become bigger than this. We're going to be taking energy away from it. So at first, we're going to have a nice positive force in the positive direction, and that force is going to get negative. It's going to slow down and stop the bullet as we go from, once we get to a certain point. And so you see now, logically, what's happening? Why would my force turn around and start pushing against the bullet as it goes down the barrel? We know that what's happening to the bullet is we have this gunpowder charge in the back of the cartridge, right? When we trigger it, a little chemical reaction goes on that's going to take a lot of solid components and turn them into gas. So I'm increasing the amount of gas behind the bullet. If I increase the number of gas molecules in here, increase the moles of gas, it's going to increase the pressure. I'm also increasing the temperature there, right? And that reaction's exothermic. Increased temperature is going to increase the pressure. There'll be greater air pressure behind the bullet versus in front, and that net pressure is going to push the bullet along. But as this goes along, it goes faster and faster. It's going to be pushing air ahead of it, right? And the faster it goes, the more air it's pushing ahead of it. That's going to start slowing it down, right? Plus, there's like friction with the barrel. Plus, eventually, I'll get to a point where this is whipping along, right? That space behind it, that chemical reaction fizzles out. Now I'm expanding that gas. Right? I'm not making any more gas when the chemical reaction finishes off. I'm assuming it's going to reach completion before the bullet leaves the barrel. That's an assumption. But the point is, wouldn't it kind of, if this was like tight fitting, wouldn't it kind of be like them trying to expand a gas? It would be like increasing the volume, which would decrease the pressure behind. You can see how if this is rubbing along the sides and the bullet heats and expands, maybe the bullet would start to rub against the sides and increase the friction force on the barrel. Anyway, the point is, overall, that friction force might end up pushing it. The total force might end up pushing against the motion and start slowing the bullet down as it goes along that barrel until eventually it would stop. And to make it to the end, someone would have had to give it an extra positive 16,667 joules in order for it to get to the end somehow. Someone would have to come along and do an extra force pushing it to get it there. All right. And so you say, well, wait a minute. When I did this first one, I got a gain of energy out going 0.6 meters, right? When you say, there must be some point where as I'm pushing, I'm doing positive work, positive work, and then I end up doing negative work, which would slow the bullet back down again. So you say, there must be some point where some length of barrel where at that point that bullet will be going the fastest. And if I cut the barrel off there, that would give me my idealized barrel length here for this case. And so you say, so what length of barrel gives the bullet the maximum muzzle velocity? And go ahead, calculate what would that velocity be. So what I'm trying to do here is I'm trying to do it's a maximum we're trying to find. So you say, oh, wait a minute, maxima and minima. I'm going to take my function and take the derivative, set the derivative to 0, find out the value that works for, yada, 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 right? I'm trying to find out what gives me the maximum velocity. Now, you'll agree here that we're working with this equation, changing kinetic energy. So I'm going to have 1/2 mass times V final squared. V initial was 0, starting from rest. I'm going to end up with this is equal to the work done. You say, no, wait. Now, mass of the bullet isn't changing, right? The bullet, that's the part of the cartridge that's going down the barrel, is the bullet. And half is a constant. So really, maximizing the V squared, it'd be the same thing as if I maximize the work, because the work is just equal to that. You know what I'm saying? So if I find out what maximizes the work, that'll be also the length that barrel that maximizes the work would be the length that maximizes VF. So I want to know the X, the final position that would maximize that work function. All right. So that is the idea. All right. So we want to maximize V final. And I can see from this equation, constant, I can see that maximizing this side of the equation would maximize this side. Maximizing the work would maximize the final velocity. Maximize the work done on the bullet. Now the work done on the bullet, that's this equation, right? And you say this equation or whatever, right? See, so if this is like the work done going from 0 to, and we would just make this a generic X from 0 to X, and we want to find the X value, right? If I did that, I put the X in, it would just look like this, right? That's what I'm going to get. You know these bounds. If I put in X and 0, right? It's just going to be this because 0 drops out. This is my equation for the work done, right? If I want to maximize a function, don't I take the derivative and set it equal to 0? But you see, but to get this, we took an integral. And integrals and derivatives undo each other. You see what I'm saying? So if I went ahead and I said, hey, I'm going to take my work, but I want to maximize the work, so I'm going to take the derivative of work with respect to position. I'm trying to find the position that maximizes it and set that equal to 0. Well, this was the integral of this function with respect to dx, get me this. So working backwards, taking the derivative of this would give me back that. You see what I'm saying? But what was that? This was the force. The derivative of work with respect to x, right, is just the force function, right? I'm just going to kick back that original function, all right? And if you think about that, 15,000 plus 10,000 x minus 25,000 x squared, and I want to take and I want to set that equal to 0 and solve for x. You say, but if you think about it, hey, does this make sense? That finding out where the force is 0 is going to be at that position where the force is 0. That's the point where the work would be maximized. you say, yeah, my force starts off being in the positive direction. And then eventually I get to a point where it will switch directions, and then the force will be going against the motion, and then it will be trying to slow the bullet back down again. So yeah, I want to do work up to the point where that force goes from being positive to where it stops pushing me faster when it gets to zero, because after that it's going to be pushing against the motion and be slowing me down. It makes sense. I'm going to get the maximum velocity where the force is zero. This is an idea we're going to use again and again. Another way of thinking about this is, check this out. F is ma, right? The force is zero because the mass is constant. The force is zero when the acceleration is zero. And acceleration is dv dt. We're trying to maximize v. To maximize a function, you take its derivative and set it equal to zero, right? The derivative of velocity is acceleration. And acceleration is that same thing said in force is zero. It's at the same point. Ta-da! Okay, so that's what we're going to do. All right, so we're going to go ahead and set this equal to zero. If I go ahead and I can solve a quadratic in my calculator, this happens to be a really easy one to solve once you see the solution. You're like, oh, when this is zero, 15,000 plus 10,000x minus 25,000x squared is when x equals 1. See, because like 15,000 plus 10,000 times 1, that's 25,000. 25,000. You get it. So it turns out x equals 1 meter. That is the length of barrel that maximizes the velocity. Again, I'd solve the quadratic if it was weird numbers. I'd have to solve the quadratic using my calculator or whatever. Okay, and now, hey, what is that final velocity that we get? We're just going to do that. Work is the change in kinetic energy. I'm going to do it over here. Sorry, I ran out of space. Work is the change in kinetic energy. My work, now I'm going back to the work equation that I got here. 15,000 plus 5,000 x squared, but the x is 1. We have a 1 meter long barrel, minus 25,000 over 3 x cubed. The x is 1, so that's 1 cubed. That's the work. That's equal to the change in kinetic energy, which is going to be 1/2 the mass. The mass of this thing was 0.1 kilograms times that final velocity squared minus the initial kinetic energy, which was 0. Okay, this is the expression I'm going to solve for V final. When I do that algebra and I do my 15,000 plus 5,000, 20,000 minus 25,000 divided by 3, right? Gives me 11,667. That's equal to 1/2 0.1 v squared. So I'm going to multiply by 2 and divide by 0.1. And then I'm going to take a square root. I get that final velocity to be 483 meters per second. That is the maximum velocity I'll get out of this, this function. All right, so that's that. I want to point one thing out to you. One more thing about this problem, and this is something that I don't really have much space. I'm gonna give myself some more paper just so I can show you this, because it does matter. I want to show you an approach that people try here at the end that is not helpful. Okay. Some people look at this and they say, oh, they gave me a force equation. So they say, okay, well, I know that F is ma. So won't I just take the force and divide by the mass? And that would be an acceleration equation. And I'll just take, and then I know that I'm trying to maximize velocity. So I'm going to set the derivative of velocity equal to 0. So I'm going to set the acceleration. So then I'll just set that equation I get equal to 0, right? And then solve for x, right? The thing about this is that what makes this not helpful is that you're going to get force in this problem was not given to you as force as a function. What am I saying here? Some people say I'm going to divide the force equation by mass and get an acceleration, and then I'll take the derivative of it to get, actually, that is what we did. Some people, okay, just a side note. Okay, here's what some people are looking at. Some people think that what they're going to do is they're going to try to get a velocity equation from the acceleration equation, right? And so what they would do, some people say, I want to do that. I know you don't need to define the max, but let's just say they did that. And so they think they're going to take a derivative of that, right? I mean, they're going to take an integral. Sorry, they're going to take an integral of that, right, to get the velocity equation, right? Do you know what I'm saying? Sorry. So where they hit a snag is in the fact that the force equation they gave us force as a function of position. But to get a velocity, I have to take an integral with respect to time. But so I have this equation that acceleration is that force, 15,000 plus 10,000 x minus 25,000 x squared. But they want to go ahead and they want to take an integral with respect to time. But you're like, well, those variables aren't the same. That's x and that's t. Can't do it. All right. Your variable that you're going to integrate has to be the only variable in your equation to take the integral. Okay. I can't have, as time goes by, this x position is changing. I can't have two different variables there. Okay, I have to have it all in terms of one variable. So you'd have to have a way to change the x into something involving t, or change the variable of integration from t to x, or change both of them into some common third variable. We were going to do a little bit with changing the variable of integration on problem 6 of this homework set. But for now, let's just say, whew, good thing we didn't have to get the velocity equation here. We can really just say, hey, when the acceleration is 0, that is actually where we're changing. When the force is 0, that's where we're going to stop pushing on it, stop pushing it faster. That's when it's going to have reached its maximum velocity. Didn't have to get the velocity equation. All right. That's all I want to point out about that problem.